All right, hey everybody, welcome back. Hopefully you enjoyed your spring break or your week off from the teleschool. We're back at it. I'm going to continue on with colligative properties. This was the last PowerPoint that you guys saw before we left. Specifically in this one, we're going to be using the math that's involved in colligative properties. And it really only has to deal with two of the four properties that we learned about, the boiling point elevation and the freezing point depression. The other ones, I just want you to know the concepts, kind of what they do, but there's no math involved with the other ones, which was vapor pressure and also osmotic pressure. So there are two slides in here that you saw from the previous. It's just a refresher in there from the other PowerPoint just to remind you what we were talking about and all that good stuff. So I'm going to go through this, kind of teach you the math portion of it to understand why boiling point can change, and then also why the freezing point can change as well. All right, the next thing that we're going to talk about is boiling point elevation. And it says on here, when does a substance boil? So think about that for a second. All right, a substance is going to boil when its atmospheric pressure equals the vapor pressure, okay? So again, when the vapor pressure equals atmospheric pressure, that's when a substance is going to boil. When you add a non-volatile solute, it's going to affect the vapor pressure, and the reason for that is that it's going to lower that vapor pressure, causing it to have an increase in boiling point. Basically what happens is when you add that solute to it, it changes the vapor pressure, so now your vapor pressure no longer equals the atmospheric pressure, causing an increase in boiling point. Okay, the temperature that can the temperature difference between a solution's boiling point and the boiling point of a pure solvent is called the boiling point elevation. That's going to be represented by the variable delta T sub B. Now we're not going to do any math today, but that variable will come back into play here again. The boiling point elevation is directly proportional to the solute's molality. We're going to be talking and using molality in these math equations because remember, molality has to deal with moles over kilograms of solvent. So we're going to be talking about that or using that variable as we go through the math. The molar boiling point elevation constant is known as K sub B. And again, it's the difference in boiling points between 1 mole non-volatile and non-electrolyte solution and a pure solvent. All right, and you should know that the boiling point of water is 100 degrees Celsius. The Kb value, so that molar boiling point elevation constant, is denoted as 0.512 degrees Celsius per mole. So that Kb value is a constant. So this constant right here is something that you guys need to make sure you know. Again, we're not doing any math today, but you will need to know it as we go forward. All right. So basically what it means is that 1 mole of aqueous solution containing a non-volatile, non-electrolyte solution or solute will boil at 100.512 degrees Celsius, so a little bit higher than it normally would. In the diagram over here on the right, again, what you can see is the one on the left, there's no solute interfering with the normal evaporation of that liquid, so those gas particles are able to escape. Over here on the right, where you can see the introduction of these little red solute particles, basically, again, they are causing a interaction with the solute, with the solvent, not allowing the solvent to evaporate like it normally would. So again, by doing that, you're going to have to change the vapor pressure, it changes the vapor pressure, making the boiling point higher. All right, the first thing that we're going to talk about today is the boiling point elevation formula. You can see that it's appearing right there on your screen for you. It says delta T sub B equals I Kb lowercase m. But before I continue, we need to know what each one of those things stands for. So the delta T sub B stands for the boiling point elevation. That's how much the boiling point is going to change. The I stands for the number of ion particles. So you'll have to look at your compound, you'll have to be able to count up the number of particles you have. The K sub B is a mole boiling point constant, which I'll show you on a chart here in a minute, and the lowercase m is for molality. So again, just like I tell you all the time, it's important that you guys know what each one of these values stands for. Each variable has a meaning to it. So again, in order to do this stuff, you got to know what that is. The other equation that we're going to use for this is BP equals normal BP plus delta T sub B. BP stands for the boiling point. The normal boiling point is a constant that you can look up again on the table, which I'll show you here in a minute. And the delta T sub B again is the boiling point elevation. So the chart that I'm going to show you, I have it here on the slideshow, obviously, but you can also find it on page 432 in your book. Let's go ahead and look at water, for example. If I find water down here at the bottom, the normal boiling point for water is 100 degrees Celsius. So if we were using the second equation, BP equals normal BP plus delta T sub B, the normal boiling point is 100 degrees Celsius. If we were using the first equation, the molar boiling point constant, which is KB, is 0.512. Now I know on the chart it says 0.51. However, the one that I gave you in the slide before is a little bit more specific, so 0.512. And again, that represents the K sub B. Okay, the next thing we're going to talk about is freezing point depression. It says the freezing point of a solution is always lower than the freezing point of a pure solvent. Again, for the same reason, adding any kind of solute particles is going to lower the freezing point, causing a change, which makes it the freezing point actually lower. The temperature difference of a solution's freezing point and the freezing point of a pure solvent is called the freezing point depression. You can see that the variable is delta T sub F for freezing point, F for freezing. For example, we should know that water freezes at 0 degrees Celsius. And the Kf value, again, that value, that constant, is going to be negative 1.86 degrees Celsius per mole. So basically what it means is this means that 1 mole aqueous solution containing a non-volatile, non-electrolyte solute will freeze at negative 1.86 degrees Celsius, okay? So again, if you add a solute to your water, you've now lowered the freezing point, so it actually is going to be a little bit lower than 0 degrees Celsius. The same idea when putting salt on the roads, it's going to lower that freezing point of the water. Again, hopefully so the thing doesn't, the water doesn't freeze. So how does this happen? If you see the diagram over here on the right, in the left one, we have our normal system where we just have the water particles in there. They come together when they form a solid called a lattice. All right, over here on the right, you can see our introduction of our red solute particles. Basically, what's happening is those solute particles are going to interfere with that lattice, making it harder for those water particles to come together. And because it's a little bit harder for those water particles to come together because the solute is kind of interfering with them, it lowers the freezing point. Okay, in this slide we're going to talk about the freezing point depression formula. So that's appearing right there on your page. Delta T sub F equals IKF M. So again, just like we learned before, we got to know what each one of these variable means. So the delta T sub F is the freezing point depression. I, again, is the number of ion particles. KF is the mole freezing point constant. M stands for molality. The second equation we have is Fp equals normal Fp plus delta T sub F. Fp stands for the freezing point, the normal freezing point of a substance, which you can find in a chart, and then the delta T sub F again is the freezing point depression. Again, I have for you the chart that's from your book here on your paper. So if we take another look here at water down here, we see that the normal freezing point of a substance of water is 0 degrees Celsius. So if we're using the second equation, that normal Fp would be 0. And then if we were using the first equation, the K sub F, the mole freezing point constant, would be negative 1.86. All right, to talk a little bit more about the equations, specifically the I in the equations, I stands for the number of particles. It says the equations given for boiling point elevation and freezing point depression specify the molality of a non-electrolyte. When electrolytes are used as solutes, you must find the molality related to the specific number of ion particles formed. So just kind of a refresher here, the difference between electrolytes and non-electrolytes. Electrolytes are going to be ionic compounds, and they're going to, when they're put into a substance, a liquid substance, they're going to dissolve and break apart into their ions. A non-electrolyte is usually a covalent compound. When you put it into a substance such as water, yes, it dissolves. However, the particles don't split up into individual units. They're still the same thing. So, for example, sugar, when you put sugar in water, it dissolves, but it's still sugar particles throughout the system. Whereas when you put salt in water, salt's an electrolyte, salt is going to break apart into its Na plus and Cl minus ions. All right, let's take a look at a couple of examples of how the I is going to be affected depending on what particle you use. Remember that I is determined by the number of particles you have, and you've got to figure out, number one, if it's a electrolyte or a non-electrolyte. But before we begin looking at these examples, I want to kind of give you a quick refresher. Remember that an electrolyte is an ionic compound. Ionic compounds are broken down into their ions, so you're going to have the I is going to change. The number of particles will change. A non-electrolyte is a covalent particle, and their I is always going to be 1. So let's take a look at a couple of examples. The first example we see, we have NaCl. Now, NaCl, you should know, is an ionic compound. Remember, ionic compounds are metals and nonmetals. So we have our Na, which is a metal, and our Cl, which is a nonmetal. So when it breaks apart, we know that we have Na plus, and we have Cl minus. So what you do to determine the number of I's, you count them up. We have one Na and we have one Cl. So our I is going to be 2. Now to determine how this affects the molality, all you do is you take your I and you're going to multiply it by the molality, which is in the problem. So we take our 2 and we're going to multiply it by 0.231, and we solve that out, and when you do, you should have gotten 0.462. Okay, so again, you can see how the molality has changed when you have NaCl. All right, let's look at our next example. We have aluminum chloride. All right, so the first things first is we got to determine, is it ionic or is it a covalent compound? You should look at it. Again, you have aluminum, which is a metal, and chlorine, which is a nonmetal. So I'm going to break it apart. I have Al, which remember is plus 3. And I have 3 chlorines, so 3 Cl minuses. So I just simply count them up. I have 1 aluminum, I have 1, 2, 3 chlorines, so grand total. Your I is going to equal 4, so I equals 4. Now again, what I'm going to do is just take that 4 and I'm going to multiply it by the molality, which is 0.231. When you solve that out, you should have gotten a new molality of 0.924. Again, when you're doing these, you've got to know the difference between ionic and covalent compounds, and you need to go ahead and make sure you know how they're going to dissociate. All right, I'm going to put up the next 2 examples. We have C2H2, and then we also have Ca3PO4. And I'm going to give you guys a minute to kind of look at these problems and try to determine on your own the I for each one of those. All right, let's take a look at this third example here. We have C2H2. So the first thing to determine is what kind of compound is this? We have C2 carbon. Now carbon, we remember, can kind of act as either in an ionic compound or a covalent. We see that it's also paired with H, hydrogen. So we have a nonmetal and a nonmetal. Whenever we have two nonmetals, we should know that it's a covalent compound, and so it is a non-electrolyte. So in this case, we don't dissociate, so our I is just going to simply equal 1. All right, so for this one, all you have to do is take 1, multiply it by the molality, which was 0.231, and you should just get the same thing. So you guys notice that the molality doesn't change. There's really no effect when you're using a non-electrolyte. Okay. The next example, we have Ca3 PO4, so it's calcium phosphate. Now again, calcium you should know is a metal, and we have 3 of those, and remember calcium is plus 2, so we have calcium plus 2. And we have 3 of them. And the other thing that we have is the phosphate. Now remember, phosphate is 1 ion. You don't split it up to P's and O's. You leave it as phosphate. Phosphate is minus 3, so we have PO4 minus 3. And PO4 minus 3. Okay, so again, count them up. We have 1, 2, 3, 4, 5. We have 5 for our I. So we just take our 5. We're going to multiply it by 0.231. When you do that, you should have come out with a number of 1.155 molality. Again, that's how you determine the I and how it can affect the molality of a substance. Remember, the important thing is you've got to remember what you're dealing with, whether you're dealing with an electrolyte. An electrolyte is an ionic compound, or a non-electrolyte, which is a covalent compound. Remember, non-electrolytes, they do not change the I. It's just going to be 1 every single time. All right, now we're going to go through a couple of these practice problems. I'm going to do the first 2 with you and walk you through them, and then the next 2 I'm going to give you some time to kind of solve out on your own, and then I'll go through them. So I have my equations here in the top right of my screen. We're obviously going to need those. Any constants I have on a separate sheet of paper. I don't have them on the screen because there's so many, but I'll make sure I note that when we go through them. All right, so it says calculate the boiling and freezing point temperatures of a 0.625 mole aqueous solution of any non-volatile, non-electrolyte solute. All right, so in this problem, it's asking for the boiling point and the freezing point. So what we're actually looking for is this equation and this equation, what I've highlighted up here at the top. Now the problem with that is that I need the delta T sub B and the delta T sub F. So I can't go ahead and solve for those 2 things without solving for the boiling point elevation and the freezing point depression. So it doesn't matter which one you do first. I'm going to do the boiling point elevation first. So I write down my equation. Now that I have my equation, I'm going to plug in what I know. For I, it says an aqueous solution of any non-volatile non-electrolyte. Because it's a non-electrolyte, remember that's a covalent bond. So our I is going to be 1. The K sub B is a constant. Now, it doesn't give us a specific solution that we have, so we're just going to assume that it's water. And remember, the boiling point constant for water is 0.512, and then obviously you see the M right here in the problem. So I'm going to write down what I have. So again, 1 is the I, the K sub B is a constant, and that's the boiling point of the water, and then the 0.625 comes from the problem. So we'll go ahead and solve this out. And I come to find out that my boiling point elevation is 0.32 degrees Celsius. All right, so now I have my boiling point elevation, so I can solve for the boiling point. So I'm going to use this equation. BP equals normal BP plus delta T sub B. The normal boiling point of water we know is 100 degrees Celsius, and we just found the boiling point elevation above. So I'm going to plug that into my equation. So again, 100 plus 0.32, and then when you solve it out, you can see our boiling point has risen to 100.32 degrees Celsius. All right, the second part of the equation we're trying to find is the freezing point. So we're going to do the exact same thing that we did in this the first half of the problem, now just with the the freezing point depression part. So let's go ahead and write that equation down. I is still going to be the same no matter what it is, because we didn't change our substance, we didn't change the solute. So our I is still going to be 1. The Kf does change, so we got to look that up for water. When you look that up for water, you find it's negative 1.86, and the molality is still the same molality from the problem. All right, so I wrote in my numbers. Again, the negative 1.86 comes from the freezing point constant for water. All right, solve this out. When I do, it comes out to being negative 1.1625. Now I was really specific here as far as my number goes. I didn't use significant figures. You guys know that I don't use significant figures a lot of times when I show my examples, because I want you to get the exact number. So now I have the freezing point depression. So I'm going to go ahead and use my next equation. Freezing point equals normal freezing point plus delta T sub F. All right, so we found the freezing point constant, so we can plug that in. The normal freezing point of water is 0 degrees Celsius, so let's go ahead and stick that into our equation. So 0 plus negative 1.1625 degrees Celsius. And again, you can see that the freezing point has lowered, okay? We call it freezing point depression, the delta T sub F, so it should lower our freezing point. So you can see that our freezing point now is negative 1.1625. Now, obviously, if I was going to significant figures, it'd just be negative 1.16. Usually in many of these problems, you're going to have to do both equations. If you're looking for the freezing point or the boiling point, you just got to be very careful with what the problem is saying. Okay, remember that if it's asking for a boiling point elevation or a freezing point depression, you're looking for the delta T. If it's asking for a boiling point or freezing point, you're using the BP or the FP. All right, practice problem number 2 here. It says calculate the boiling point elevation of a solution containing 50 grams of glucose dissolved in 500 grams of water. Calculate the freezing point depression for the same solution. Okay, so for this problem here, what we're looking for is the boiling point elevation, which is this top equation, and the freezing point depression. So these are the two things that we're really looking for in this equation. So I don't need the other two equations for right now. So it says calculate the boiling point elevation. So the first thing I'm going to do is write down my equation. All right, it says that we have glucose. Now, you should know that glucose is a covalent bond as you look at the equation for it, C6H12O6. So you should know that I is going to be 1. Again, I gave you water, so you know that your boiling point elevation is going to be that 0.512. The last thing we have to figure out is the molality. All right, so for molality here, the problem is it doesn't specifically give you in the equation. So you've got to remember from our last last set of notes with concentration, how to find molality. And remember that molality is moles of solute over kilograms of solvent. So I have 50 grams of glucose. I'm going to have to change that to moles. So that's what I'm going to do first. So 50 grams of glucose divided by the molar mass of glucose gives me how many moles I have. So now I have moles. Now I've got to divide that by the kilograms of solvent. So I'm going to change my 500 grams of water to kilograms. And I'm going to plug this into my next equation. So you can see molality equals moles of solute over kilograms of solvent. Okay, so again, the 0.2776 comes from the moles of glucose. The 0.5 comes from the kilograms of water. So 500 divided by 1,000 gives you 0.5. Solve that out. When you solve that out, you should have gotten 0.55 mole solution. Okay, so this 0.55 mole is going to equal the lower case m here. So now I have all my numbers, so I'm going to plug them in. All right, so again, 1 comes from glucose because it's a covalent non-electrolyte. The 0.512 comes from the constant boiling point for water. And the 0.55 comes from what the molality we just solved, so we go ahead and solve it. You can see our boiling point elevation is 0.284 degrees Celsius. All right, the other half of the equation is the freezing point depression. So again, start off with writing your equation down. After you have your equation, you have the I is going to be 1. The Kf is going to change. Remember that's negative 1.86 because we're using water, and the molality we found above. All right, so I got all my numbers, I plug them in. When I plug them in, I solve. And I found the freezing point depression to be negative 1.03 degrees Celsius. All right, on to practice problem number 3 here. A lab technician determines the boiling point elevation of an aqueous solution of a non-volatile, non-electrolyte solute to be 1.12 degrees Celsius. What is the solution's molality? All right, so think about what you got. You're looking for a lowercase m. I'm going to give you a few minutes to take a look at this one and try to solve on your own before I put up my answer. All right, so let's take a look here. In the problem, it gives you a boiling point elevation, and you're looking for molality. So what I'm going to use is this top equation right here, because it gives me, again, boiling point elevation. So I'm going to go ahead and write that equation down. All right, so let's see if we can figure out the other parts. The delta T sub B, it tells us in the problem, is 1.12 degrees Celsius. The I, it says we have a non-electrolyte solute, so I is going to be 1. Again, it doesn't give us a specific type of liquid, so we're just going to assume that it's water. So the K sub B is going to be the 0.512. And then, of course, we're solving for M. Okay, so now I have all the stuff that is in my equation. So now I have to go ahead and solve for the M. So basically, all I'm going to do is take the 1, multiply it by the 0.512, then divide both sides by the 0.512, and you should come out with a molality of 2.19. All right, here's our last practice problem, number 4. Says calcium chloride is often used to prevent ice from forming on the roads during winter. What are the boiling point and freezing points of a 0.029 mole aqueous solution of calcium chloride? So in this problem, what we're going to look for is the boiling point and the freezing point. So it's very similar to problem number 1. I'm going to let you guys take a few minutes to go ahead and try to solve, and then I'll come back in a minute. All right, so let's take a look at this problem here. Again, we have calcium chloride is used to prevent ice from forming on the roads during winter. We have a 0.029 mole aqueous solution, and we're looking for the boiling point and the freezing point. So we're looking for this up here and this down here. But remember, in order for us to do these problems, we have to have the delta T sub B and the delta T sub F. All right? So we need to have those first, but in order to get those, I have to use the other two equations. So the first thing I'm going to do, just by habit, is solve for the boiling point elevation. Okay, so we have an I. I is the number of ionic molecules. So in this problem, we have calcium chloride. Now you should know that calcium chloride is an ionic compound, which means it's an electrolyte, which means our I is going to change. So what I need to do is I'm going to break up the calcium chloride into its ions. So you can see up here above, I have calcium chloride. It breaks down to Ca plus 2 and 2 chlorines. So again, I have 3 total ions. So I is going to be 3. The K sub B, again, it doesn't give us any other specific solvent or solution. So we know it's going to be water, so that's going to be 0.512. And then our molality gives us in the problem is 0.029. So we're going to go ahead and put that into our equation. Now that we have that into our equation, we can solve for the boiling point elevation. You should see that the boiling point elevation, after you solve this out, comes out to being 0.0445 degrees Celsius. Now again, I know I didn't use significant figures. I'm just trying to be as accurate as possible when I use these numbers. So that's why I have that. Now I can go ahead and solve for my boiling point. The normal boiling point of water we know is 100 degrees Celsius. That hasn't changed. So we're going to take 100 plus our new boiling point elevation, solve it out, and again I got 100.0445. Now again, I want these things to be as accurate as possible. So for our PowerPoint here, I'm giving it to you in the exact number and I'm not changing to significant figures. All right, the second half of the problem is to find the freezing point. So we're going to start it off the same way. We're going to find the freezing point depression. Again, my I is still going to be 3. My Kf does change. Remember, the Kf for water is negative 1.86, so that does change. And then my molality is the same molality as above. All right, so now I have my numbers. I'm going to plug them in. When I plug them in, I find that my freezing point depression is negative 0.162 degrees Celsius. Okay, I then take that and I put that into my second equation. And the normal freezing point of water we know is 0 degrees Celsius, and the delta T sub F we just found. So plug those numbers in, and when you solve, you can see that the freezing point changes to negative 0.162 degrees Celsius. All right, if you had trouble with any of these problems, please go back and watch this video a couple of times, or at least kind of the last half of the video. Obviously, if you have any questions, please reach out to me and I'll help you out.